And you're good to continue.
Copy, go to continue.
There's-
You have the go.
There's a total of 4 mechanisms that do the launch lock. 2 are at the hinge where the, which is actually closest to us in the display, at the joints, 1 at the top, 1 at the bottom, and then 2 kind of hold the wing back to keep it from rattling during launch. At the far corners
I
of
can
the
confirm and
side mirrors.
go to arm.
Copy, go. You have the go to arm.
I can confirm armed, waiting for the stored command sequence enable.
I think that's so amazing to me is that what's happening today is the end of 178 release mechanisms. You know, every single one had to work.
Yeah, all stations. Our next go.
Incredible.
We'll fire OTE LRM Group 8. OC, you are go to fire.
Roger. CC, you have the go to fire. Copy, go.
Yeah, there was a lot of work to put into these. A lot of people have heard about our single point failures. Each one of these itself was a single point failure. In other words, if one of those 4 launch releases does not release it, we're not able to move this side of the mirror forward into position. So this would be our last of these 4 single point failures. There's still other single point failures and some that stay with us for the life of the mission. Different areas of structure or a method fails, we don't write down. But these are major milestones in getting the observatory into its final configuration.
For those of you who are joining us, you're looking at live coverage of the commissioning of the James Webb Space Telescope. Today we are unfolding the second of the wings of the primary mirrors. Joining me is Julie Van Kampen. She is the deputy commissioning engineer. You can see people there excited and happy.
Mom copies. Thanks, Step Lead. Glad to have the plot so we could follow along. We share your enthusiasm. That's awesome. 178 out of 178. Congratulations. Thanks.
They just fired.
It confirms that all of those
And they
mechanisms fired, 178 of them. Over
Yep,
the
and
course
I
of
could
the
hear
last
on the
I see this is
news.
step ops on ops. I see that proc has completed. We're ready to continue with 693.032 DEU to standby.
Copy that.
And they could see indications in
And the command
telemetry
line looks good. You're good to execute.
Copy, CC, you
that
have
everything
the go
is
to
successful.
execute. Executing.
And you're good to continue.
You have the go to continue.
The next couple steps are going to be getting the motors ready again. So before they checked them out, they had to put them into a standby mode while they were doing the firing. That was the safe configuration that you heard the deployment lead speak to. Now they're going to get them back into the configuration, and then they'll get ready to do their first small move.
OC, I can confirm we're in standby round robin. We're ready for 693.033 to restore default torque limits. The command line looks good. You're go to execute.
Copy. CC, you have the go to execute. Executing.
And you're go to continue.
Copy, go to continue.
And earlier we had mentioned the position called MOM. That's the Mission Operations Manager. And the elbow we're seeing in the top screen, and that's Carl Starr. He's the MOM of JWST. When they do the small mirror move, the small motor move on the mirror here, in our our tool that we get to see on the screen, the OVT, the Observatory Visualization Tool. We don't actually, it's such a small move, we won't see the tool actually change at all. It won't be until the major move before we can actually see it on this tool. And it looks like they're calculating that's going to be another 20 or more minutes until we actually see the full move take place.
Right. We're sitting here now. We're actually watching the mission operation manager, and you'll also be seeing live coverage from the MOC, the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm there as well, although in an isolated conference room, so I can speak to you unmasked. Of course, we're operating under COVID protocols, which has made a challenge, but it's a happy and festive day here, and we're really looking forward to this next deployment. Later on in the program, we'll have a chance to take some of your questions from social media, and today we're asking you to use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse. We'll be stopping our commentary as we hear commands. So, we may have a conversation, but then we'll stop to hear how the commands are progressing. As first they make a very small movement to make sure the wing is moving correctly and all the motors are functioning correctly. And then in about 20 minutes from now, you will see on the left-hand side of your screen, you will actually see the wing click into place. And then after that, there will be a couple hours of latching it, of making sure that this is fully in its extended permanent configuration. I see Julie's got a big smile on her face, which I love to see, because it's a lot of work.
So,
up at the top there, we're
again,
looking at Bill Oakes. Yeah.
Yeah.
Bill Oakes is the program manager, and you'll see him throughout this. As Julie said, he's sort of the head of the mission. Everybody kind of reports to him at this point. There's an interesting teamwork between scientists and engineers on a mission like this. And actually, Julie and I were talking about this earlier, that, I come from the background of being an astrophysicist. And when I think about Webb, I mainly think of all of the incredible data and the questions, the scientific questions that I'm looking forward to being able to explore with the telescope. Julie has a very different perspective. Julie, tell us a bit about your position as the deputy commissioning engineer. Tell us about what that job entails.
Sure. As the deputy commissioning engineer, I've worked to try to make sure all of the various pieces that it takes to commission the telescope come together in a way that makes an engineering sense. So there's a lot of people who have worked many, many years to make sure that it comes together operationally, working with how the commands are sent, how the control is done of the observatory, making sure our communications with the SN is worked out and timed with all of our activities. But I deal with the engineering aspect of that to make sure that if things are happening in a faster sense, that will still be safe. Like our operations can be handled 2 days earlier or 2 days later, should the timeline move one way or another from a hardware perspective. So many people are very interested in how the science will work, but I'm interested in how the parts of the telescope work themselves to make sure that they work together to actually give you that science.
Thank you. And that's the question, of course, about how you become an engineer or how you become a scientist. What is your background? I mean, what do you have a degree in, for example, that led you to this particular job?
My actual degree, both my undergraduate and I have a master's degree in mechanical engineering. And basically I started off being interested in how to design and build things. As a kid, I liked to build forts. You name it, I like to put it together. So I went to school to be a mechanical engineer, graduated from school. My first company was a small was a small company, so it kind of got to do a little bit of everything. So you kind of learn to be the Jill of all trades. And from that, I moved to NASA and got into the testing department and was able to do actually a lot of the Hubble servicing missions from the testing side to get those instruments and components that were being sent to Hubble on the different servicing missions ready for those missions. Then eventually I moved over to JWST, and I've been on JWST since 2003. And I've been a systems engineer on the instruments and then the payload and now onto the commissioning.
Wonderful. So we will pause our commentary when we see your commands from the Mission Operations Center, but we do have time to take a few questions on social media. So whenever people ask questions like this, I'm touching wood right now. It says Nicholas on Twitter asks, would the observatory still be operational if one or a few of the mirrors break? Is there anything out there that could break them? So, I mean, so that there's maybe a couple of different ways to answer this. I mean, what happens? All of the mirrors will be aimed independently. What happens if, for example, one of them doesn't aim correctly?
The great thing about the Webb telescope is with these independent mirrors is that we can handle so many different scenarios like that. For instance, if one of the mirrors either, let's say, a piece of debris hits it, or during its launch and ascent phase, some of the stresses were higher than predicted, and we had a problem that broke a mirror or an actuator behind the mirror. We could actually take that mirror essentially out of the image by making it very much out of focus with the rest of the telescope. And, if anyone's ever experienced having a floater in their eye or something like a scratch on your eye, you can realize how much you can see. And it is completely unaffected by that. So when something's not quite in sync with the rest of the primary mirror, there's different ways to take that impact out. Some of it's physically by moving the mirror out of its focus, and some of it's digitally by knowing that there's a imperfection that's going to be in each and every image that gets subtracted out digitally from those images.
Thank you. Yeah, maybe another social media question. For those of you that would like to actually have questions answered live on air with us, use the hashtag #UnfoldTheUniverse. So we'll be looking for hashtag #UnfoldTheUniverse to take your questions on social media. And so this actually kind of goes along with the second one. So Michael on Facebook asks, what protects the mirror from micrometeors and other fine space dust debris? I think the answer is not much.
Nothing. What you see is what you get. The sun shield is facing the Earth and the sun. So not only does it protect it a little bit from a little bit of possibly dust or anything coming from the sun, but the heat of the sun is basically what it does. If the sun shield itself, this isn't quite the question he asked, but if the sun shield itself got hit by a micrometeoroid and got a little tear or a rip in it, that's part of why we have 5 layers, and we can tolerate so much damage throughout time. And that was part of our lifetime calculations to make sure, based on our little bit of knowledge that we have of other observatories at the L2 point, to make sure that the environment there can be sustained by all of our optics and all of our sun shield over the time span that we expect to be there.
And just to give you an update, you're looking at live commissioning of the James Webb Space Telescope. From what I understand, there will be a call in about 4 minutes, release larger mechanism. About 4 minutes after that, we should be able to see the wing start to move. So now in a bit under 10 minutes, we'll see the wing move.
Yeah, that first release.
Copies. At this time, we're ready to continue with 693.034 DEU to operate frame 6.
Copy
What
that.
they'll do is,
Command line looks
With
good.
the-
You are go to execute.
Copy. To see how to go to executing.
And you're go to continue.
Copy, go to continue to see how to go.
the small move, this will verify for sure and for certain that all of those launch release mechanisms have released and that the mirror is free to move into its final position.
Right. Continuing our conversation, I mean, some small impacts from micrometeorites will happen. You know, over the
Yes.
lifetime of the mission, there will be some damage to the mirrors of the telescope. I remember at the Goddard Space Flight Center when they replaced some of the cameras on the Hubble Space Telescope. They brought some of the old cameras back for
And
analysis.
DevOps can confirm operations frame 6. And we're ready to continue with the small motor move. So we're ready to go at 693.039.
Copy. This on the window.
That command line looks good. You're go to execute.
Copy that. CC, you have to go to execute. Executing.
And you're go to continue.
Copy, go to continue. CC, you have to go to continue. Copy, go.
And stand by while we review parameters.
Copy that. Send them.
So we were talking about the debris. Also being at L2 is very
I see
useful.
the parameters look good. You're go to move the motor.
Copy that. CC, you have to go to move. Copy, go. And pro complete.
DevOps copies, and you can queue up the stop.
Copy that.
And the motor status is moving.
Copy.
Seeing at Goddard, I remember the cameras being brought back for analysis. They were analyzing every tiny little crater that was made by a little piece of dust or a little piece of debris. So, but you said that L2, for example, is actually a very nice place to be. It's actually a kind of a cleaner place when it comes to space junk. Is that correct?
Yes. Low Earth orbit, which Hubble is in, has a lot of space debris, as everybody has seen. I think it's gravity.
And OC, you are go to execute stop deploy.
Copy that. CC, you have to go to execute. Execute.
And you're go to continue.
So,
Copy, go to continue. CC, you have to go. Copy, go.
stopping the motor move now.
And I see the motor is stopped. At this time, we're ready to continue with 693.041 DEU to standby. Clock looks good. You are go to execute.
Roger. CC, you have to go to execute. Execute.
And you're go to continue.
Copy, go to continue. CC, you have to go. Copy, go.
Once they've taken a moment to analyze their telemetry and then move on again with the mirror moves, they're going to take the motor and they're going to drive the mirror up against a hard stop. Once they move it up against the hard stop and they verify that they're happy with that position, then they're going to start moving some latches into position. But when they move the latches into position, they'll kind of back off on that deployment motor a little bit to make sure that the latches are the ones that.
Okay, DevOps can confirm standby round robin. At this time, we're ready to continue with 693.042 to restore the gain stat parameter to default. That command line looks good. You are good to continue.
Roger, sir. CC, you have to go to continue. Executing.
And you're going to continue.
Copy. CC, you have to go. Copy.
Sending some configuration commands to the motors.
So once again, you're joining us for the live commissioning of the James Webb Space Telescope. The starboard wing of the primary mirror is being deployed today. In just a few minutes, we should be able to actually see it moving. On the left-hand side of your screen is a real-time visualization based on telemetry, based on data from the telescope. It's generated by a computer. This is not a camera. We do not have cameras, unfortunately, on board Webb, but this will show us the configuration that's actually in real time. And in just a few minutes from now, we will begin actually bringing that side part of the primary mirror around to form one large mirror of 18 segments. The segments that you see are colored gold. We'll talk more about the mirrors after we do this deployment. We'll have some time as the into its final configuration. But that is actual gold, very, very thin coating of gold, just a few hundred atoms thick. And the telescope would actually look quite a bit darker than you see it in that animation. The sun shield is blocking out all of the light from the sun and any reflected light from the Earth and the moon. And so those mirrors right now are exposed to the dark, cold space that it will be doing its primary science, looking out into the universe. I understand the call to move is imminent any moment now. And when the mirror begins to move, we will just all sit back together and enjoy watching that. And we'll come back with commentary after that has completed. And we have some time as the latch telescope, a couple of hours into its final configuration. So we'll have different guests and experts to talk about what's going on when that happens. I'm joined by Julie Van Kampen, and she is the Deputy Observatory Commissioning Engineer.
RTCP is complete.
DevOps copies. It looks like that load completed successfully. We're ready to continue with 693.043 DEU to operate frame 6.
Copy that. On the window.
And the command line looks good. You're go to execute.
Roger that. Lucy, go ahead and execute.
Executing. So they've just put the
And you're
mirror
going to
back.
continue.
Right.
Copy that to continue.
The deployment motor back into its operational state. It was taken out of operational state to do a reconfiguration. And now it's ready to do the full move once this is done.
We're coming to you live from the Space Telescope Science Institute in Baltimore, Maryland. This is happening in real time. The James Webb Space Telescope commissioning, the final wing of the primary mirror. You're looking at live coverage from the Mission Operations Center, the MOC. And the command to deploy the wing is imminent. We're waiting for it any minute now. And then we will a visualization tool to see that. It'll just be a couple of minutes, something like 4 to 5 minutes. And then after that, we will come back with more commentary about the observatory, and we'll talk to some of the people that are some of the science leads as well about some of the scientific questions this observatory has been designed to answer.
They've just given the
Stand by
command
while we
to
review
go
the
ahead.
parameters.
Okay, standing by.
They're reviewing the parameters to move
Okay,
the mirrors.
I see those parameters look good. You are good to move the motor.
Copy, go to move to see how to move. There you go.
And this will move the mirrors into their final position.
Now complete.
The screen to the right shows us our ground station.
And the motor status is moving.
You can see the mirrors move in the visualization tool. It will take about 4 minutes for them to completely come forward.
And a reminder, this is real live footage. There's a 3-second time delay. It takes that long for light to travel at 186,000 miles per second. The James Webb Space Telescope is now well over 600,000 miles away.
And
Thing to remember about this.
Go ahead.
I was just going to say, just remember that this visualization is real. This is not pre-recorded. It's based on actual data coming to us from the telescope, being downloaded right now.
And the important thing about the light delay is not that the light takes that long, but the data, which moves at the speed of light, takes that long to come to us. I know that was a question we had on some of our social media before.
Ops with the status, we have started our deployment into the deployed hard stops, and our current looks really good, nice and low.
Mount copy.
That was another of our deployment engineers confirming that everything looks good with our mission operations manager.
It's exciting to actually see it moving. You know, there it is on the visualization tool. It's getting closer and closer.
Yep, it's going to be momentous when it finally comes into position.
The first wing was successfully deployed yesterday, and now this is the final part, the primary mirror being put in place. Julie, give us a sense of the scale. These mirror segments. I mean, I had the honor of watching this being built, a lot of it at Goddard. How big across, for example, is one of those hexagons?
They're about 1.5 meters across from tip to tip. The hexagons are quite large. It's amazing to actually be in the clean room and look up to see the whole mirror assembled, towering above you. There's no amount of seeing it on photos that kind of gives you the sense of actually standing next to it in our clean room when it was assembled. And as we talked about before, and once it's fully into position here, the final shape that our primary mirror is going to be called a tricontagon. It's about a polygon.
The step lead on ops are about 3/4 of the way through the deployment, and everything still looks really good.
And the mirror itself will be concave. You can sort of just see that in this simulation. They actually have simulated some stars and things in space that you can see moving on the surface of the mirror. Also, as the mirror comes forward, and I'm not sure that we can see it at this angle, but there's a thing called the bat wing, and it's a shade that falls down behind the mirror to help shade any light that might be coming up through the hole in the sunshade from keeping any of the backside of the telescope warm. There's one on each side that comes down passively as the motor moves this forward. And then the gaps between the mirrors are very small. I think it's on the order of several millimeters.
This is step lead on ops. We have reached the end of deployment, and we are preloading into the latch pads.
All right.
Okay, copy.
You see people clapping? Yes. Wonderful.
Yeah, everyone's up on their feet and clapping.
Wow, just look at that. The primary mirror is successfully deployed. This is a first. We have made a space observatory the mirror was so large that it had to be folded up to fit inside the rocket.
Hey, OC, at this time we're ready to continue with 693.046. Enable activate SCS 256.
Okay, copy.
And that command line looks good. You're go to execute.
Copy that. See, go ahead and execute. Execute.
think you can hear the relief in our deployment ops
And you're going to enable activate.
Copy, go to enable.
voice.
Copy, go.
I just feel this kind of glow, you know, in my chest right now, just seeing that mirror all deployed all together. The size of a mirror allows us to collect more light from fainter objects, and in a lot of cases that means farther away objects that light took many billions of years to travel to us. A chance to see the universe as it was perhaps only a couple 100 million years after the start, after the Big Bang. The sensitivity of this mirror will allow that. And the size of the mirror also gives us a clearer, higher resolution, able to see more detail in space than ever before. So this was something that absolutely had to happen. You know, we had to unfold this mirror. The secondary focusing mirror had to come out, and then a little bit more than a week ago, the amazing sun shield, and there it is in front of us. You're looking at this animation. This is not a pre-made animation. This is based on actual data coming from the telescope to us right now. We are live at the Space Telescope Science Institute, and we have successfully unfolded the last part of the primary mirror. After this, are still more commissioning acts to come, very important ones, for example, focusing.
Okay, DepOps can confirm that 256 is active in the delayed state. And I've confirmed with the Dep lead, they're ready to begin the 3-door latch off stow and latch to safe. So we're ready to continue with 693.048, move 1 of 20.
Copy that. On the window.
And that proc looks good. You are going to execute.
Copy. Is you happy to go to execute? Executing.
Just started our deployment.
Copy, go to continue.
Go through a mouthful of description there of what happens next. A hook latch, and it's basically really that. It looks like a big latch, like you would hook possibly on a bathroom door or a tie down. If you had tie down straps to hold some packaging onto a vehicle, it's actually a hook. And you heard her call it 3-door, and what that means is it's essentially it has a couple of different degrees of motion that it can do.
Stand by for parameter review.
Copy that. Standing by.
Each of the latches are a little different in which degrees of freedom that they can move in, and so the 3-door
and
is
OC, the parameters look good. You're going to continue with the motor move.
Copy, go. You see, you have to go to continue.
Is one of the types that we have.
This latching procedure will take a couple of hours. We will be here through the entirety of it. We will be able to tell you when it is complete. And we may pause our commentary now and again, but we'll have different guests talking about aspects of the engineering and science of the James Webb Space Telescope through the next few hours. And this procedure will take quite a while. Can you tell us a little bit more about the latching, what we're going to be witnessing in the next few hours, Julie?
Sure. There's actually several latches. The next one that you'll hear her talk about will be one of the 2 doors, and there's 4 in total, I believe, and each of these will come into position, and then they'll very slowly. They want to make sure that they don't do something that's called like over-constrained. And as anyone who understands how a mechanism might move, you can easily kind of get yourself jammed into a position if you try to tighten one thing before you're completely aligned with another. Almost like when you change your tire, you want to kind of do that star pattern to wiggle it into just the right position to make sure it's flat. You don't want to tighten one of those bolts before you get the others snug, and you want to tighten them up in a pattern. So they'll do the same thing with these latches. They'll make sure that they're done in a very precise order, that the different degrees of freedoms of each of the latches are coming into play in the order that they had planned, to make sure that they get that mirror latched in and locked down in the absolute best position, so that those mirrors are in range for what they need to do for actually defining the surface of that mirror with the actuators and motions that will come next in the next couple of weeks.
Well, Julie, thank you so much for being with us through this procedure. We're going to come back to you later on as this happens. At the moment, we are going to have one of our expert guests come up. We're going to be joined by
that motor move looks good. We are ready to continue with 693.049. 3-door latch to safe, move 2 of 20. And the command
Thank you for
line
having me.
good. You're go to execute.
Copy that. Susie, go ahead and execute.
Executing.
And you're go to continue.
And we'll come back to you later.
So you have the phone.
Absolutely.
Copy, go.
The next person we're going to be talking to is the Associate Administrator for Science at NASA, Dr. Thomas Zurbuchen. Thomas, it is wonderful to see you. How are you feeling? Tell me about what you just observed.
Oh, I'm emotional about it. What an amazing milestone. We see that beautiful pattern up there in the sky now, almost complete. Of course, it needs to latch, but what an amazing milestone just ahead of it. 178 out of 178 of these actuators that had to fire the right way. I'm just so amazed and in awe about this team.
So one of the things that I'm just sort of, I haven't seen you for a while without a mask. They have us all in isolated rooms, and you're always clean shaven. You look a little bit different today. Is there is there some story behind that?
You notice, right? So, basically what happened is after we launched, frankly, I told my wife, I'm not going to shave until this entire telescope is fully deployed. This is like my favorite sports team. When they're in the playoffs, right? You have to be sure that you fully support them. So that's what I'm doing here. I can't wait to shave. Michelle, my wife says, are they done soon?
And so I mean, that actually gives us a chance to talk a bit about what's coming out next. So, about how long do you think it's going to be until you shave?
Well, I fully expect, assuming that everything goes well today, I fully expect to shave today. And I just want you to know, this team is basically on track within a half a day or so of the fastest schedule that we had outlined. Frankly, I sat there today with some of the managers and said, if you ask somebody, 2 months ago, even a month ago, hey, we're going to be done by the 8th of January, what would we have said? I said it's massively optimistic, frankly unrealistic to assume that. I think this team is just incredible. Back to my sports analogy, we're seeing that the team on the playing field, and it's just an awesome team, and frankly, kind of over and above all expectations that anybody might have had.
You're talking about the team, and all coming together, but then there are also some tremendous challenges that this team has faced. And, I know that that's something that you've been there with the team for quite a while now. Can you give us a sense about, I mean, not only did we have COVID, where we were all trying to do this and be isolated and be careful for each other's safety and all that, but there were all kinds of, in your on this mission, you were like, wow, I'm amazed they overcame that.
Look, I just want to tell you first, Michelle, I'm very humbled to be part of this team right now. And I know so many others were part of this team for decades before I even showed up. I've only been part of this team for 5 years, and I'm honored to be part of the team. Yes, we've had a number of challenges. If you, of course, look at everything that, go backwards, anything with the deployments, some of the challenges, frankly, that the team immediately addressed, they made it look easy, even though some of these challenges, frankly, were tough. You go back in time, and of course, it's very hard to think about the grit of this team that we're seeing without thinking of COVID, right? I mean, what's really amazing is how they overcame that, right? How they did not, they took every excuse they could to stay on track, right? It's so often, Michelle, we sometimes we see teams, in our private lives or even, elsewhere where all of a sudden, people take excuses to not fulfill goals. This team found every excuse to do so. You go back in time and you realize, how hard it is to be truly a single team. And Michelle, it's not just the engineers, it's on Capitol Hill who are allocating the budgets, the people in the White House, all the stakeholders there. And I think what Greg Robinson, and for me, it's just really important to say that name, what he managed to do and kind of overcame is really building a team from the top all the way to the technician, the single team. And of course, that's why it's going so well, right? Because of, unified teams, are a beautiful thing to watch.
This is the depth lead on ops with the status. We're a couple minutes into our move to the safe position on the 3-door latch. Everything looks really good. Strains are low, and the strain offset came in right where we wanted it. So we're looking good.
Mom copies. That's awesome, Dep Lee. Keep going.
So as the Associate Administrator for Science at NASA, you are a scientist, and there's some incredible scientific goals with this mission. And like we said, that this all started from questions. We launched the Hubble Space Telescope. We understood there was so many more things to see, even farther back in time. Give me a sense about some of the science that you're most looking forward to. Hopefully that this mission will accomplish.
How much time do you have, Michelle? Right, I'm going to give you like a couple. But I've been doing a lot of reading and thinking about this kind of early universe and the first galaxies, and for me, the potential impact of primordial black holes in this whole discussion, really the relationship of galaxies and black holes that are so tight. As we look at today's galaxies, kind of in our neighborhood, like how did that go there? For me, it just boggles my mind, to think of these enormous structures in the universe that are in the past. I'm going to give you a second example, Michelle, and of course it's about finding life elsewhere, but I'm going to focus on our own solar system. We're going to make observations, for example, of Europa. We did that with Hubble. And there's amazing papers out there in Nature and Science that says just marginally we can see kind of emissions of Europa that kind of are similar to Enceladus, for example, where water from these subsurface oceans is coming out together with organics at Enceladus. The question is, does that happen with Europa? And of course, we're moving towards a launch of Clipper in 2024, and we want to make sure that if there are such, emission points, that we know that, because we want to take the measurements with that amazing mass spectrometer on Clipper. And there's similar type of discussions on Mars, where, of course, we're in the middle of another huge adventure, trying to get these samples back in the first round trip to another planet. And for me, again, observations of the Martian atmosphere, its composition, and its dust components are just so critical.
This is something that I think that, I really enjoyed seeing your leadership on in the last years is no mission stands alone. We have missions, each one supports the other. It's not just this mission, then that one. There's a strategy that everything works together. So like you said, for exploring the solar system, you have something like the Webb telescope, which from a distance can see things like Mars, Europa, places like Titan. But then we have missions that are poised to go there and explore closer up as well.
Oh, I strongly believe that, right? What's so beautiful about nature and so amazing about the science program we have at NASA is the interconnectedness between the different questions that are there. And to me, that has always been one of the most exciting parts of studying nature, is to see relationships that were not innately recognized there. And I think the more we learn about nature, and especially in astrophysics, the more we see some of these connections, right? I'm always in awe. I read some papers, not as many as I would like to, Michelle, but nonetheless, I read some of the papers. I realize that atmospheric models of exoplanets so often are done by our good people in Earth science, because they know how to do it in ways that nobody else can. So yes, they belong together, all these missions, because nature is also interconnected.
Haven't changed significantly.
Absolutely. Listening to the commands from the mock, making sure we stay up to date on them. But absolutely. I mean, you mentioned the first stars. And there's probably plenty of people in the audience that don't really know your background as a scientist. Maybe you get a little sense about your scientific expertise and how you came to be Associate Administrator of NASA.
Well, so I studied astrophysics, and I was really inspired by some of these missions. Frankly, I remember when I was 8 years old, I got this book about the Voyager missions and some of these telescope that Nancy Grace Roman, right, it really started imagining. It was in the 70s when I got this book, and that inspired me out of the little mountain village in Switzerland to be where I am right now. I'm an astrophysicist, but I mostly focused my work about the sun and kind of the inner solar system. So I know how to do mass spectrometers, and I've worked with teams. And what I fell in love with, Michelle, is really the ability of working with amazing teams. When I see a team, whether it's in athletics, or whether I see it in this control room right there, a team that is truly operating at their highest capability, I'm so excited to see it. It's the most beautiful thing, but it gives me so much hope of all these other things we can do. So when I look at astrophysics, of course, I think of the classes and so many of the things that I learned in the late 90s that are no longer true. And that's what science is about, because we learn all the time. And can you imagine, even in 5 years from now, how classes everywhere around the world will be affected by this very amazing observatory that's being set up right now?
Yeah, there's going to be some very, very profound things. I mean, you were talking about looking at some of the first galaxies to form. And this, of course, is one of the reasons why we have an infrared telescope, which is different from Hubble, which was largely in visible light. Infrared actually allows us to see, to some extent, farther back in time, farther away in the universe, where the expansion of the universe has actually stretched out the light from visible light into the infrared wavelengths. And you mentioned this close relationship between black holes and galaxies. I mean, a lot of our viewers out there probably don't realize that we are orbiting around a giant black hole right now at about 500,000 miles an hour, the giant black hole in the middle of the center of the galaxy. And there seems to be some relationship between how galaxies form and how black holes form. But there's a real mystery about these big black holes that we see so far away and therefore so far back in time. Maybe give us a little more sense about, this is one of the things that as an astrophysicist, we look at and we say, I don't understand how that happened.
Right, it's truly a chicken and egg problem, right? Kind of right now, it seems to be the case that black holes and galaxies really coexist, right? It's actually really hard to find a galaxy in which there's no black hole there. It really seems that it's a really important part of the galactic evolution. But how does that start? Is the black hole first? What is the role of the black holes? From the beginning. You talked about the interconnectedness, Michelle. We're right now setting up a small telescope we launched a few weeks ago, IXPE, the Polarimetry Explorer, and hopefully next week we'll be able to give kind of first light of that kind of X-ray observation, kind of again providing new insights about some of these kind of more recent black holes, kind of really trying to understand what the mechanisms really are, and that in those black holes, but also the environment around it. For example, the roles of magnetic fields that are so critical in so many of these
things. Is when you're looking at the universe, in the case of Hubble, we've how did such a huge black hole form that quickly? And as an astrophysicist myself that studies stars, one of the things that I'm hoping Webb will shed some light on is the fact that the very first stars in the universe might have been quite different than the stars today. And maybe that's something you can give us a little bit of an idea. Why would the first stars be that much different from the stars we see around us right now?
I think it's a really great question, and I think it's one of the most amazing parts of really talking about how we relate to our universe. And that is that, of course, when the universe starts at the beginning, the atoms that form really are much less rich in terms of diversity than we have today. On my hands, I have gold and platinum rings that my wife gave me, and we know that those are not from the beginning of the universe. Frankly, they come from neutron stars that are merging, that are much, much later, kind of after a lifetime of a star. So when you look at the first stars, like what you have, kind of the material you build with is much lighter than stars that are that most of the stars that we're looking at night through a telescope, because those stars are next generation stars in so many of the cases with much heavier components that are there. So the question really is, how do you build those first stars? And frankly, how do they then kick off that evolutionary process? There's a lot of models, and the data will, of course, constrain these models. That's what we call learning, right? If it's, say, this model is correct, this model is not correct. And by the way, there's an observation that none of the models predicts, which is the element of surprise. We can always bet on the element of surprise, Michelle. Frankly, often the surprising parts are the most important ones.
I sort of like that. We're talking about the history of chemical elements, but in there is always the element of surprise. Yes, the universe began, with hydrogen and helium, a tiny little bit of a couple other elements. But as you mentioned, everything that really makes us up, the things that make up a human body, like carbon or the calcium in our teeth, or phosphorus or sulfur, the things that we need for our DNA.
We have completed this move of the 3-door latch to safe. So we're going to proceed with the 2-door latch.
One of the things that we're really hoping that the James Webb Observatory will shed some light on is what the universe was like before most of that formed. I mean, really the origins of the stuff that we are coming from. But there's another part of our origins too. You mentioned, in 5 years' time.
Ready to begin the 2-door latch off stow. As the motor moves 3 of 20.
Copy that. CC, go ahead and execute. Executing.
And you're going to continue?
Copy go. CC, you have the go to continue.
One of the things that I'm really looking forward to is being able to maybe in a few years from now point to a star in the up in the sky and say that there's a planet around that star that has an environment similar to us here on Earth. Maybe to take us through how will Webb do that? How will Webb be able to explore what the actual environments on planets that far away around other stars? How will Webb be able to do that?
So if you go back in time of the Earth, of course, long before we were here, our planet was very different. And frankly, the emergence of life on the atmosphere here, in that Goldilocks zone, right, where water can cool. The emergence of life really changed the atmosphere. Frankly, there's a number of papers out there that said a large fraction of the nitrogen in our atmosphere may very well be from the emergence of life. There's other, of course, elements, oxygen type of, ozone, elements like that really come, of course, are very much part of that cycle of life that is here. So as we look at other planetary atmospheres, right, the question really is, what are the patterns there? And can we find patterns that are indicative of the presence, both the ability to have life there, but even in some cases, the follow-up or the consistency with life there, certainly from what we've learned here, but perhaps also other versions that we yet have to learn. Of course, what's so hard about life is we have n equals 1. We know only one life. All life on Earth is related, and we learned a lot when we went from one solar system to many solar systems, stellar systems. Frankly, many of the models crumbled within weeks of the first observations that were published in 1995. So when we look at life, similar things will happen. For me, that's why that's so exciting, Michelle.
Well, that's absolutely wonderful. So once again, we're speaking to Dr. Thomas Zurbuchen. He's the Associate Administrator for Science at NASA. Thomas and our audience out there, we're going to take a short break. We're going to take a pause in the commentary, and we will be coming back at 11 o'clock in the morning Eastern Standard Time to resume our commentary. But Thomas, thank you so much for joining us. What an exciting day, as you said, very emotional. And I'm just so pleased to be able to be here on the floor beneath you. So I'll wave to you from down in the building.
Yeah, that's true. And I thank you for all that amazing, Michelle. It's been wonderful. I've watched you many times from different locations. I know you have exactly the same passion I do about this amazing science, and you can't wait to get those data back in just a few months' time.
Absolutely. Thank you so much for joining us, and we'll be back in our commentary in just a few minutes.
Thank you. Yeah.
Okay, and OC, that motor move completed successfully. We're ready to continue with 693.052. Two-door latch to safe, move forward 20.
Roger that. That is on the window.
And that command line looks good. You're go to execute.
Copy. CC, go ahead and execute. Execute.
And you're go to continue.
Copy, go. CC, you have the go to continue.
And stand by while we review the parameters.
Both C, standing by.
And OC, the parameters look good. You're go to continue with the move.
Copy, go to continue. CC, you have the go. Ready.
And OC, the motor move is in progress. This will take about 14 minutes.
Copy, 14 minutes. We'll stand by.
depth lead on ops with the status. We are on step 4 of 20 of latching. We're latching the 2-door to the safe position. Into it a couple of minutes now. Again, strains look really good, nice and low, and our strain offset is matched our predicts, so no updates required there.
Excellent. Mom copies. Thank you.
This is Ocean.